The next type of rigid motion we're going to talk about is called a translation. Sometimes it's called a slide, but we usually refer to it as a translation. So a translation just shifts the image. It doesn't reflect it, it doesn't rotate it. So the image is going to have the same orientation and look exactly the same. It's just in a different location. So if you look at image, the pre-image ABC, and if you want to explain what happens to ABC to move it to A prime, B prime, C prime, well, let's just look at where A is going, or actually let's look at what happens to B. B is shifting, if I count left and then down, 1, 2, 3, 4, 5, 6, 7, 8. So we can say you're going to move the entire image left 8 and down 4, because not only does B move that way, but so does A and C. So we move left 8, and down 4. And that's all we did. So we have translation notation to use. And the notation can be represented a couple different ways. Capital T represents translation. And in this case, if I'm moving left 8, the x value is first. So I could say -8, comma, and then -4. We always put the x value first. Another notation is using the rule. So if I start with xy, I'm going to end up at x minus 8 and y minus 4. And you're going to see both types of notation used in this class. So is the size of the object preserved under translation? Did this thing change size? If you look, the answer is the size did not change, so the size is preserved. That's a yes. Size is preserved. And then the order of the vertices, if I look at that, A, B, C, if I'm looking at the order, the way they go around, this is going around this way, and A prime, B prime, C prime is the same thing. So the order is also preserved. So that's another yes. So when we look at the vocabulary today, we want to define something called an isometry. And an isometry is a transformation that does not change in size. So an isometry does not change in size. These include the rigid motions, reflections, translations, and rotations. All three of those are called isometries because they don't change the shape and the size of the image. Now we have direct isometry. A direct isometry preserves the size and the orientation of the vertices. And then an opposite isometry changes the order of the vertices. So an opposite isometry is going to be your line reflections. A translation is, since it doesn't change the size, a translation would be direct. And a line reflection would be opposite. If you look at that, if I think of a line reflection, if this is A and B and C and you reflect it over that line, now things are labeled in the opposite direction. A prime, B prime, C prime, and if you think about the way the letters are going, A, B, C is going around like that, and in this case it reversed the order of the letters. So that is an opposite isometry. Okay, so we have the same image that we had in the opening exercise, and what we're going to do is we are going to connect with rays the pre-image to the image. So what that means is I'm going to start at A, and you're going to use a straight edge. I'm going to start at A, and I'm going to make a ray, which is an arrow, to A prime. And then I'm going to do the same thing at B. I'm going to arrow to B prime, and C, I'm going to arrow to C prime. Now if you look at those three rays, they have common properties, and if you look at them you should see that they are parallel to each other. All the rays are parallel. So I can describe this translation that moved left 8 down 4, I can describe it with what's called a vector instead, which is what this ray is that we created. A vector is a directed line segment that has both length and direction. If you remember, what was that movie, whatever the movie was with the minions, the guy's name was Vector, and he had both magnitude and direction. So magnitude is the length of the vector, and direction is the angle at which it's pointing. So I can specify a translation with a vector instead of a coordinate pair. So this part is super easy. You need a straight edge, and all we're going to do is draw the vector. We're going to say that the pre-image is the solid line and the image is the dotted line. So if I'm going to, I'm going to say that pre-image is solid. That's my starting point. All I'm going to do is draw the vector that represents that translation. So you pick any point on the pre-image and you draw the ray to its image, the corresponding point on the image. So for the first one, there he is. That's all you got to do, only you're going to use a straight edge. The second one, you pick any point and draw a ray to its corresponding point. There's that vector. The third one, the vector can be represented right here, but anywhere, any point drawn to its corresponding point, and you're going to have parallel lines. So that's pretty easy. Now we're going to work some examples using our translation rule. So if I have this, capital T represents a translation, and I want to move x by an amount of a and y by an amount of b. This is applying this rule to this coordinate. Here's where you end up. You end up at x plus a and y plus b. That's how you apply the rule. So we're going to work through some of these examples in class, or here, and then we'll do some more in class. The first one, determine the coordinates of the image of this point. So here's my original point, here's my rule. So I'm going to add -2 to 5, and I'm going to add -1 to -3. So if I write the rule down, t of -2, -1, here's the notation. I'm applying that transformation, and I'm applying it to the point 5, -3. That's going to end up being the same as 5 plus -2 and -3 plus -1. So your final answer ends up being 3, -4. That's what you get when you apply this rule to this point. I'm shifting this point to the left 2 and down 1, and that's where you end up. So now we have different notation, but we're going to do the same thing, and I'm missing my subtraction sign there. Let me fix him. That should be y minus 1. There you go. So we have determined the coordinates of the image of point -8, -3 under this translation. So here's a different way to write the rule. Whatever my x value is, I'm adding 4. Whatever my y value is, I'm subtracting 1. So that's what we do. -8 plus 4, there's my x coordinate, and y, and -3, -3 minus 1. So my final answer here is going to be, -4 and -4. The third example here, we're going to determine the translation that maps the point from -5,5 to the point 7,1. So here we're going to create the rule. And you have to think to yourself, well, what am I going to add to -5 to get to +7? So the rule, if you think about it, is I've got to get from -5 to +7, I got to move 12. So I'm going to move 12 in the x direction, and then in the y direction, to get from 5 to 1, I've got to move -4. If you can either think about that in your head, or you can subtract the points. 7 minus a -5 is 12. 1 minus 5 is -4. Either way, your answer is this, 12, -4. For the next example, we're going to create the rule and then apply the rule to a new point. So an image maps the point -2, 5 to -4, -4. We got to create that rule and then apply it to this point. So again, if I take my answer, -4 minus a -2, That means I got to move by -2. For the y values, I have -4 minus 5, so I got to move by -9. My rule is -2, -9. Now I'm going to apply that rule to the image 1, 4. So once I do that, I end up with an answer of 1 minus 2 is -1, 4 minus 9 is -5. So that's how you find the rule and apply it to a new point. And then the last one is drawing the vector. Translate the image 1 unit down and 3 units right. So if I draw the vector first, let's just pick any point. Here's what my translation vector looks like. I'm going to move 1 unit down and 3 to the right. So my vector looks like this. And you have to put an arrow at the end point. That's important. You're going to lose points if you don't put the arrow and if you don't put it in the right place. So everything is going to move 1 unit down and 3 to the right. So since we have a grid to help us, I'll just start moving this guy. A moves 1 down, 3 to the right. There's A prime. B is 1 down, 3 to the right. There's B prime. 1 down, 3 to the right. C prime and D prime. And you can use a straight edge. Mine doesn't work so well on this grid. There's my new image. So that's what translations off the coordinate plane look like. And again, if I were to connect B to B prime with my translation vector, this vector is going to be parallel and the same length as the original vector that I drew up here. And that's true in every case. Connecting any point to its image is going to yield the same vector in translations. Now in class we're going to practice how to do translations, how to construct them, which is a little bit more complicated, which is why I can't really show this to you in the video. So we're going to work on that in class.